All right, so now I want to talk about substitutions in specific cases. So the first thing I'm going to talk about is in square planar complexes. Let's compare octahedron and square planar. A square planar complex doesn't have as many ligands around it, right? So it tends to be that square planar reactions react by associative mechanisms because there's two whole planes where a ligand can come in. And then an octahedral complex will end up giving you most of the time a dissociative reaction. So if you compare the two, it's pretty easy to see what happens. But the square planar often, not always, but often, happen by an associative mechanism. So I'm going to write a general reaction here. I'm going to use platinum as my example. One of my ligands I'm going to represent with a T, and the other one's going to be X. My entering group will be Y, and this will be the reaction that I'm talking about for the rest of the time that I'm talking about square planar reactions. So again, typically these are associative mechanisms, and so the nature of Y affects the rate. So for platinum specifically, we know that it depends on Y because the rate varies with the identity of Y. It tends to be that if Y, this is from data, chlorine as your entering group is relatively slow. And there's a trend that follows that iodine is faster. Ether groups are faster than iodine. So chlorine, iodine, oxygen, sulfur, and phosphorus. Oxygen, sulfur, and phosphorus don't have negative charges in this case. And so as this trend goes from left to right, we're actually getting softer in our ligands. So in this case, you can actually make a relationship between hard-soft acid-base character and the identity of the leaving group, the identity of the entering group. You could also do the same thing with the leaving group. So the trend here follows hard-soft acid-base because platinum is soft. So when you're comparing individual ligands and with metal interactions, often the two things that really matter are nucleophilicity and hard-soft acid-base matching of the entering group. Did you talk about nucleophilicity in organic chemistry? Okay, good. So in square planar complexes, there's something called the trans effect. And the trans effect is talking about this ligand that I wrote as a T that's trans to the leaving group. So it's important that whenever we're speaking about the trans effect, it's understood that we're talking about the ligand that's trans to the leaving group. It turns out that the ligand that is trans will influence the rate of the reaction. So trans ligands will influence the rate of the reaction. And there's two reasons or two ways that this happens. The first is so the trans ligand will speed up the reaction by weakening the metal ligand bond. So I'm going to call it the MX bond. So I'm talking about this bond here. It follows that trans ligands that are strong sigma donors will weaken the metal X bond. And they make the rate faster. So the reason that this is because the trans ligands, the trans ligand and the leaving group are actually sharing a metal d orbital. So if I define my axes here as y and x, I'm going to draw my dx squared minus y squared orbital on the metal. So my ligands were up here, and then I had my X group, which is leaving, and my trans ligand across from it. So this trans ligand is donating electron density into the orbital right across from the X group. And the more electron density you put into that orbital from T, or from the trans ligand, the less the X group, or this ligand over here, will be able to donate electron density. So things that are good sigma donors over here, it strengthens the T metal bond and it weakens the bond across from it. So again, we're using thermodynamic arguments to understand kinetic observations. So this is a thermodynamic factor, but again, when you increase the energy of the reactant, which this is doing, basically it's making this bond here unstable, then you increase the energy of the reactant and it decreases the activation energy. So whenever you decrease activation energy, you increase the rate. So the trans effect works through weakening metal leaving group bonds through this sigma donation. If the trans ligand is a pi acceptor, though, it can also increase the rate through a second type of, well, it's like, I guess you could call it a second type of mechanism, and that is its mechanism of action is by stabilizing the transition state. So the trans ligands that are strong pi acceptors stabilize the transition state, and then they lower the energy of that transition state. Now, this is specific for the type of mechanism for square planar complexes. The fact that the mechanism is associative allows this statement to be true. So what happens here is you have the metal, and I'm just going to draw one of the orbitals. So if you have your entering group Y coming in here, and you also have your leaving group in there still, remember that the associative mechanism means that you form a complex of higher coordination number. So you're going to be having basically this extra Y ligand coming in. When your trans ligand is a pi acceptor, so I'm just going to draw a pi system over here. This is your pi star. When it's a pi acceptor, it takes electron density off of that metal ion and stabilizes the extra electron density that's being put onto that metal ion by this incoming ligand. So this incoming ligand is adding electron density to the metal, which is stabilized by this pi accepting trans ligand. Does that make sense? Do you want me to write it down? Okay. So pi acceptors take electron density off of the metal center. As your incoming ligand, or in this case Y, enters, it puts more electron density on the metal center. I'm going to call this extra electron density. And that extra electron density is destabilizing. So as Y comes in, the trans ligand is stabilizing that extra electron density. So as Y enters, it puts extra electron density on the metal center, which is stabilized by the pi accepting ligand. So depending on how you draw this, and it's really hard to draw this in 3 dimensions, but you could have Y and X sharing the same orbital that's pi accepting to this trans ligand. But the idea is, I mean, without even thinking about symmetry, you can just understand that the trans ligand is accepting electron density from the metal. As that extra ligand comes in, then you're adding electron density to the metal that's unstable, but it can be stabilized by that trans pi accepting ligand. Your textbook has a diagram of this kind of interaction where Y and X are also pi interactors, but they don't need to be. I think it's a mistake in your textbook. Okay, so overall, this is the trend with trans ligands. So the overall trans effect follows like this. So water is about the same as ammonia. Chlorine with a negative charge is a better sigma donor. A carbon with a negative charge is a better sigma donor than that. Phosphorus is better. And now we go to pi accepting ligands. CO, Cn minus, and ethene. Things on here are sigma donors, and these things up here are pi acceptors. The sigma donors give you a trans effect, and relatively though, in this series, this is the weak trans effect. Pi acceptors give you a stronger trans effect. So as we go from left to right, we're going faster. In general, ligands that increase the delta are also going to increase trans effect. We're not talking about delta O here because these are not octahedral complexes, but the same things that increase delta O will increase the delta for a square planar complex. And if you look along this series here, this actually follows the spectrochemical series to some degree. So the sigma donors are weak on the trans effect scale, and then the pi acceptors are stronger. Other considerations that don't have to do with the trans effect. Remember, again, we're talking about square planar that are associative reactions. If you have bulky ligands, it slows the entering group. So it slows your entering group, which I'm going to call Y, and therefore it inhibits your reaction. Or it inhibits, more specifically, associative reactions. So, for example, if I had a platinum that had, like, let's say you had a T-butyl group over here, and then P with, like, tri-isopropyl phosphine P. If you had really bulky ligands, because this mechanism, so let's say this was our leaving group, Y is not going to want to come in there because it's bulky, okay? An interesting part, or an interesting feature of these reactions is that the stereochemistry is often retained. So Y, or the entering group, will replace X, the leaving group, in the exact same position it was. And the reason that that happens is, one of the explanations that we have is that it goes through a trigonal bipyramidal intermediate that is not long-lived. So if I write this reaction again, the associative reaction where Y comes in, let's see here. So your X, Y, and trans ligand are basically in the equatorial plane of a trigonal bipyramidal intermediate. So this is your 5-coordinate intermediate. And so basically, if I was going to draw this as an organic chemistry mechanism, I would have my Y group coming in, making this intermediate, and then X group leaving. And the Y simply replaces the X in the exact same position. Now this is the case most of the time, but not always. Do you remember us talking about the Berry pseudo-rotation? I just mentioned it and I told you to read about it in your textbook. The Berry pseudo-rotation is something that happens to trigonal bipyramidal geometries. And basically it's when, I'm going to draw this in pink, it's when one of these ligands, so an axial ligand and an equatorial ligand basically switch, they kind of just rotate. And if that happens, you will get a change in the isomer, like you basically will get isomerization. So when you see an example where the stereochemistry is not retained in a square planar reaction, it's because this trigonal bipyramidal geometry, this intermediate, is long-lived. So if it lives long enough, then it can isomerize. So if this thing is long-lived, isomerization will happen. So you can see figure 21.5 in your textbook if you want to see what that looks like in a cartoon. Now let's talk about octahedral complexes. And as I mentioned earlier, this often happens with a dissociative reaction. The exception here is for big metals. So if the metal ion itself is big enough, it provides a sphere that's big enough where the octahedral ligands aren't very close to each other. And if the metal ion is big enough to accommodate a 7th ligand, then it can do an associative reaction. So I'm going to abbreviate octahedrons like this ML5X. If it's a dissociative, you will form a intermediate of lower coordination number, and then your entering group will come in. And for dissociative reaction, remember the rate depends on the nature of X, or the identity of X. For dissociative reactions in general for octahedral complexes, there's something called the linear free energy relationship. It's just the relationship between the log of the stability constant versus the log of the rate constant. So there's a lot of relationship basically between the thermodynamics and the kinetics of these reactions. And for this reason, you also have a correlation between hard-soft acid-base theory and kinetics. Now, when it comes to the identity of the ligands around the leaving group, strong sigma donors as ligands facilitate MX bond breaking. So if we look up here at our reaction mechanism, as X leaves, now you have an intermediate of lower coordination number. So this intermediate has very low electron density, so you could call it an electrophile. The more the ligands themselves are sigma donors, the more electron density that they're putting, those ligands, which I've represented as L, the more that they interact with the metal, the more electron density that metal has. So it stabilizes the intermediate if you have strong sigma donors, and it makes the reaction happen faster. Sterics also come into play here. In this case, it's the opposite of square planar. Bulky ligands actually increase rate. And that's because they increase steric strain in the starting material. So the original octahedral complex, if it has bulky ligands, they're sterically strained, and that steric strain is usually relieved somewhat in the intermediate here, the ML5. So when you go to a lower coordination number, it's more stabilizing due to sterics. These bulky ligands, the bulk is also referred to as cone angle, especially when you're talking about PR3. So for trialkylphosphine ligands, so I'm going to just draw one of those interacting with a metal ion. So it's a phosphorus with 3 alkyl ligands. Here you could think of this as a cone, and the cone angle is basically just this angle here. The bigger the cone angle, the more bulky. And for octahedral complexes, we already kind of mentioned this last time. But we didn't use these terms. There's something called ligand field activation energy, and that ligand field activation energy is simply the change in the ligand field stabilization energy from the starting complex to the transition state, and that's so the ligand field stabilization energy of the transition state is represented like that. So you subtract the transition state energy from the complex stability, and you get your activation energy. And as far as stereochemistry goes for these octahedral complexes, they go through a square pyramidal transition state or a bipyramidal transition state. So when they go through a square pyramid, so this is a picture of a square pyramid, stereochemistry is retained, and so the entering ligand will replace the ligand that left in the exact same position. But when you go through a bipyramidal transition state, you can see isomerization. Now, isomerization in octahedral complexes does not need to, you don't have to go through a substitution reaction to actually have isomerization. So without substitution, isomerization happens by a similar mechanism. So if I had a metal complex where I'm going to put my 2 X groups trans to each other, and they're in an octahedral, so I'm just going to put a square around for the equatorial ligands. I can arrange this, or I can have the X group leave. If I go through a trigonal bipyramidal transition state, the X group can come back in in the equatorial plane, and that's what usually happens. So the isomerization in this case isn't necessarily because of a Berry pseudorotation. It's because the group that's entering comes in from the plane or the equatorial plane and gives you the isomerized product. When I say isomerized, I mean that the entering group does not come into the same place as the leaving group left. Does that make sense?